Chapter 2, AC Power. In order to work with the tools of electrical measurement, we have to make sure we understand the difference between scalars and vectors. So just a quick review here. A scalar quantity is a quantity that has magnitude only. And some of the examples of scalar quantities are length, area, volume, speed, mass, density, temperature, pressure, energy, entropy, work, and we've shown a diagram of volume here. Vector quantities are scalar quantities with direction. So there's a direction associated with a magnitude. And some vector quantity examples are displacement, direction, velocity, acceleration, momentum, force, electric fields, and magnetic fields. And we are also going to add to this in electrical quantities, voltage, current, and impedances. But they have a special name, which we're going to see in a very short order in the next few slides. In a power system, a power source will supply a voltage that is sinusoidal or a sinusoidal in wave shape of a particular frequency. And in our case in North America, that is 60 cycles per second. The voltage starts at 0, peaks at plus A, travels through 0 and peaks at negative A. Then returns to 0 volts, and it's repeated 60 times a second. When mathematically modeling a sine wave, such as V is equal to sine omega t, it can be done and considered to be directly related to a vector of length A revolving in a circle with an angular velocity of omega degrees per second. V can be represented by a revolving vector. Its magnitude is said to be A. Its angular velocity, omega, and omega is in degrees per second, and you could also describe it as 60 cycles a second, but in this case we're just talking about angular velocity in degrees per second, such that the angle of the vector at any particular time is given by the product of the angular velocity times time. So if the angular velocity is in so many degrees per second and we multiply it by number of seconds, it will come out to a value of degrees, and that will be the angle that the vector forms with the horizontal. In a utility power grid, omega is 60 cycles per second, at least in North America. In Europe and some places in South America, they use 50 cycles per second as a standard. However, here in North America, it's 60 cycles a second. All voltages and current are rotating vectors. All are rotating at the same angular velocity, and all may be mathematically dealt with, but must follow the rules of vector analysis. With these special properties for vectors, they are sometimes renamed phasors. What is the difference between a vector and a phasor? A phasor is a special type of vector. Vectors have two values, magnitude and direction, whereas phasors are vectors that rotate at system frequency. Phasors are relative. If there is more than one phasor that we are studying or looking at, they are all rotating at the same system frequency, or they will all have the same angular velocity, or all phasors are displaced by a fixed angle of separation. Comparison and analysis is then done by stopping the rotation at some point. The relative position of each phasor is unaffected by when the rotation is stopped. So even though phasors are rotating at system frequency at all times, all the analysis and comparisons that are done using phasors are done at a particular instant in time. In other words, when they are stopped. When working with phasors, the most common descriptive form is polar notation. Polar notation is where phasors are described by the length, which is called the magnitude, and its angle, or its relative displacement from 0 degrees, or the horizontal, denoted by the angle symbol that looks like this. For example, this phasor would be designated 8.49 in magnitude and at an angle of 32 degrees. Standard orientation for phasor angles in AC circuit calculations define 0 degrees as the right horizontal, making 90 degrees straight up, 180 degrees to the left, and 270 degrees straight down. Note that all phasor angles represented in polar form can be positive when measured counterclockwise from the horizon, or the horizontal, or negative when measured clockwise from the horizontal. For example, a phasor angle 270 degrees straight down can also be said to have an angle of minus 90 degrees. Here are some examples of phasors noted in polar notation. Notice there's two ways to designate certain phasors. The top left-hand one, we've already looked at something similar. It's 8.49 at 45 degrees. The phasor in the top right-hand corner is 8.06 at minus 29.74 degrees, or it could be 8.06 at 330.26 degrees. Both notations are correct. The one in the bottom left-hand corner is 5.39 at 158.2 degrees, and the one in the bottom right-hand corner is 7.81 at 230.19 degrees, or 7.81 at minus 129.81 degrees. Something else to note while describing phasors in polar notation is that the magnitude, we've described it as simply 8.06 or 8.49 or 5.39. Notice I haven't indicated whether that's inches, feet, meters, or it could be miles. It's irrelevant, and it could be whatever you want it to be, because the magnitude can be scaled, and it doesn't change the direction of the polar notation at all. It just changes the magnitude, and the magnitude can be scaled. So 8.49 could represent inches, feet, centimeters, miles, whatever you happen to be measuring at the time. Of course, once you pick one, all the rest are scaled to that relative amount. So if you're talking about inches, all of your phasors have to be in inches. If you're talking about feet, then all your magnitudes should be represented in feet. Another way to describe a phasor is by rectangular notation. In rectangular notation, the phasor is taken to be the hypotenuse of a right-angled triangle, described by the lengths of the adjacent and opposite sides. Rather than describing a phasor's length and direction by denoting magnitude and angle, it is described in terms of how far right or left, or how far up or down the phasor is from the origin. These two-dimensional figures, horizontal and vertical, are symbolized by two numerical figures. In order to distinguish the horizontal and vertical dimensions from each other, the vertical is prefixed with a lowercase j. This lowercase letter does not represent a physical variable, but rather is a mathematical operator used to distinguish the phasor's vertical component from its horizontal component. When placed in front of a vector, it swings that vector through 90 degrees counterclockwise. As a complete complex number, the horizontal and vertical quantities are written as the sum of two vectors. The horizontal component referred to as the real component, since that dimension is compatible with normal scalar real numbers, and the vertical component at 90 degrees to the real component is referred to as the imaginary component, since that dimension lies in a different direction, totally alien to the scale of the real numbers. Here are some examples of phasors in rectangular notation. Notice this time there is only one way of designating a phasor. So the one in the upper right-hand quadrant is 4 plus j3, which means it's a quantity 4 along the real axis and 3 in a positive j direction or straight up and down. The phasor in the upper left quadrant is minus 4 plus j3, which means it is described as minus 4 along the real axis and plus 3 along the j-axis. And finally, in the bottom right-hand corner, we have a phasor which is 4 minus j3, which means it's 4 along the plus real axis and it's 3 in the minus j direction along the j-axis. So we have seen that a phasor can be described in one of two ways. You can either use polar notation on a polar plane, such as we see here, or we can use rectangular notation, as you can see here. Notice that where we have not moved the vector or the phasor, it has remained in the same position. So you can uniquely describe a phasor in one of those two ways. So there must be a way of translating or converting rectangular notation to polar notation and polar notation back to rectangular notation. Converting from polar to rectangular and vice versa is a very simple process, and it can be demonstrated with this phasor here, and I've described it in both terms, both rectangular and polar form for convenience. So let's say we have the phasor in polar form, and we want to convert it to rectangular form. So that is, we have 5 at 36.87 degrees, and we want to convert it to a rectangular form. The real component of the polar form you can take by multiplying the polar magnitude by the cosine of the angle. So you take the magnitude 5 and cosine of 36.87, which is equal to 4, and that will give you the real component of the rectangular form. To find the imaginary side, you take the magnitude or the length of the magnitude of the phasor 5, and you multiply it by this time the sine of the angle, which is 36.87 degrees, and that equals 3. So that will give you the imaginary component, and you have to remember to put the j operator in front of it, of course, and whether it's plus or minus will fall out of the calculation. Now this time we want to go in the other direction. We want to change the rectangular form to the polar form. And you can find the polar magnitude through the use of the Pythagorean theorem. The polar magnitude is the hypotenuse of a right-angled triangle, and the real and imaginary components are the adjacent and opposite sides respectively. So the length would be the square root of 4 squared plus 3 squared, which comes out to 5. And then to find the angle, all you have to do is take the arctan of the imaginary component divided by the real component, or 3 over 4. The arctangent of 3/4 is 36.87 degrees. If two AC voltages 90 degrees out of phase are added together by being connected in series, their voltage magnitudes do not directly add or subtract as in the scalar voltages in DC. Instead, these voltage quantities are complex quantities and must add up in a trigonometric fashion. A 6-volt source at 0 degrees added to an 8-volt source at 90 degrees results in a 10-volt at a phase angle of 53.13 degrees. Vectors as well as phasors can be moved around a plane as long as their direction and magnitude are maintained. You add two vectors or phasors by placing the tail of one on the head of the other, then connecting the other head and tail, just like in the picture. Compared to DC circuit analysis, this is very strange indeed. Note that it is possible to obtain voltmeter indications of 6 and 8 volts respectively across two AC voltage sources, yet only read 10 volts for total voltage. With AC, two voltages can be aiding or opposing one another in any degree between fully aiding and fully opposing inclusive. Without the use of phasors, complex numbers that is, notation, to describe AC quantities, it would be very difficult to perform mathematical calculations for AC circuit analysis. In this example, I demonstrated adding two AC voltages together that happen to be separated by a phase angle of 90 degrees, which made the arithmetic fairly easy when we were dealing with phasor quantities in polar notation. However, adding and subtracting of complex numbers is much easier if you're able to convert to and from polar and rectangular notation, because the addition and subtraction of phasors in rectangular notation is very easy, and the multiplication and division of phasors in polar notation is the easiest form. So what you want to do is you want to add using rectangular formats, and you want to multiply using polar formatting. So when dealing with addition and subtraction of phasors or complex numbers, which phasors are, you simply add the real components of the complex number to determine the real component sum, and you add the imaginary component to determine the imaginary sum of the phasors. So in our example, we have 3 here. We have in the first example on the left, you have a phasor 2 plus J5 added to 4 minus J3, which would give you the resultant phasor of 6 plus J2. The middle one is 175 minus J34. When added to phasor 80 minus J15, you'd end up with 255 minus J49. And the last one, minus 36 plus J10 added to a phasor of 20 plus J82 gives us a phasor that would be minus 16 plus J92. So when subtracting complex numbers, it's almost as simple as adding them together. You either subtract the real components and the imaginary components to come up with the real and the imaginary component of the resultant. Or another way you can say it is you can change the sign of the phasor that you want to subtract. As we're doing here, we're putting a minus sign in front of the brackets, which essentially changes the sign of the terms inside the bracket, then just add them together. Either way, you will come up with the same answer. So in the first example, you got a phasor 2 plus J5, and you're going to subtract the phasor 4 minus J3. So you could change the sign of those components. Minus 4 would be minus 4 plus J3. Then you would take 2 minus 4 is minus 2. Then you'd take plus J5 plus J3 would be J8. In the middle one, you got 175 minus J34, and you're going to subtract 80 minus J15. So you could change the sign of that phasor. So now you would have minus 80 plus J15. So 175 minus 80 would be 95, and minus J34 plus J15 would give you minus J19. And finally, in our last subtraction, you would have a phasor minus 36 plus J10, and you're going to subtract 20 plus J82. So you change the signs of those two components of that phasor, so you'd end up with minus 20 minus J82. So you'd have 36 minus 20 would give you 56 for the real component, and plus J10 minus J82 would give you minus J72 for the resultant. For multiplication and division of phasors, polar notation is favored over rectangular notation because it's much easier to deal with. When multiplying complex numbers in polar form, we simply multiply the polar magnitudes of the two complex numbers to determine the polar magnitude of the product, and we add the angles of the complex number to determine the angle of the product. So let's look at a couple of examples. If we had 35 at 65 degrees multiplied by 10 at minus 12 degrees, you'd multiply the two magnitudes to end up with 350, and you would add the two angles together. So 65 minus 12 would give you 53 degrees. So the resultant would be pretty easily calculated, is 350 at 53 degrees. Another example would be 124 at 250 degrees times 11 at 100 degrees. So you multiply the two magnitudes, ending up with 1,364, and you would add the two angles together, so you'd end up with 350 degrees. Or you could describe it as minus 10 degrees as well. So you would add the angles together to get the resultant angle, which is 350 degrees. So your resultant would be 1,364 at 350 degrees, or 1,364 at minus 10 degrees. And our final example is a simple 3 at 30 degrees times 5 at minus 30 degrees. You'd end up with multiplying the magnitudes together, you get 15, and you would add the two angles. 30 minus 30 gives you 0. Division of polar form complex numbers is also very easy. You simply divide the polar magnitude of the first complex number by the polar magnitude of the second complex number to arrive at the polar magnitude of the quotient, and subtract the angle of the second complex number from the angle of the first complex number to arrive at the angle of the quotient. as in these examples. 35 at 65 divided by 10 at minus 12, you divide 35 by 10 and end up with 3.5 as the magnitude, and you subtract minus 12 from 65. It's the same as adding 12 to 65, giving you a resultant angle of 77 degrees. In this example, we have 124 magnitude at 250 degrees divided by a phasor with 11 magnitude and 100 degrees. So divide 124 by 11, it gives you 11.273, and you subtract 100 from 250, it leaves you with 150. And the final example is our simple 3 at 30 degrees divided by 5 at minus 30 degrees, gives you a result of 0.6 at 60 degrees. To obtain the reciprocal or invert a complex number, simply divide the number in its polar form into the value of 1, which is nothing more than the complex number 1 at 0 degrees. So in these examples, if you want to invert the phasor 35 at 65 degrees, you'd put 1 over 35 at 65 degrees, which is the same as dividing 1 at 0 degrees by 35 at 65 degrees, and that would be 1 divided by 35, which would give you the magnitude of 0.02857, and you'd subtract 65 from 0, which would give you minus 65. In the next example, you'd have the reciprocal of 10 at minus 12 degrees, which would be 1 at 0 degrees divided by 10 at minus 12. 1 divided by 10 is 0.1. 0 subtract minus 12 degrees is 12 degrees. And the final example, the reciprocal of 0.0032 at 10 degrees would give you 1 divided by 0.0032, which would give you 312.5, and then you would take 0 and subtract 10 degrees, which would give you minus 10 degrees. So as you work through a long string of complex numbered arithmetic, always add and subtract in rectangular form, then multiply and divide in polar form. It will be necessary to convert from one form to the other as you progress through these calculations. However, with the invention of the smartphone and laptop computers, there's lots of apps out here that'll do that hard work for you, but it helps to know the process so that if you run into a problem, you can always find out what's going on. These are the basic operations you'll need to know in order to manipulate complex numbers in the analysis of AC circuits. Operations with complex numbers are by no means limited just to addition, subtraction, multiplication, division, and inversion. However, virtually any arithmetic operation that can be done with scalar numbers can be done with complex numbers. When considering two sine waves that are not in phase, one wave is often said to be leading or lagging the other. This terminology makes sense in the revolving phasor picture as shown. If the rotation is stopped, we can see that the blue phase is said to be leading the red phase, or conversely, the red phase is lagging the blue phase. These phasors could be current or voltage, or one of each. If the blue phasor is current and the red phasor is voltage, the current is said to be leading the voltage, or conversely, the voltage is lagging the current. Let's look at the voltages and current phasors with a resistive, inductive, and capacitive load. For a pure resistive load, the voltage and current are in phase, and they can be represented on a phasor diagram as overlapping each other. As you can see here, they are rotating counterclockwise with 60 cycles if you want, or just omega. For a pure capacitive load, you will find that the voltages or the voltage, lags the current by 90 degrees, as depicted by the phasor diagram here. For a purely inductive load, you will find that the voltage leads the current by 90 degrees. So in the case of a pure resistive, capacitive, and inductive load, the current reacts in quite a different manner for each of those separate loads. The resistive load having the current in phase with the voltage. The voltage leads the current in the case of inductance, and the voltage lags the current in the case of capacitance. Now let's look at the voltages and current phasors with inductive and capacitive loads, this time with some resistance introduced into the circuit. Just for comparative purposes, I am re-showing the results of a pure resistive load where the voltage and currents are still in phase. For a resistive plus a capacitive load, the voltage still lags the current, but less than 90 degrees this time. And similarly, for a resistive plus an inductive load, the voltage still leads the current, but again, less than 90 degrees. In these AC circuits, these combinations are known as impedances and are denoted by the letter Z. Impedance impedes the flow of current in a circuit similar, but not the same, as resistance in a DC circuit. Impedance is a vector which is made up of two components, a resistive component and a reactance component, the reactance denoted by the letter X. Resistance is unaffected by system frequency. However, the reactance is affected by system frequency, and it depends on whether it's a capacitive reactance or an inductive reactance. For the purposes of metering in a power system that has 60 cycles per second, we don't usually worry about the frequency because that remains unchanged when metering. It is usually constant at 60 cycles per second, or if in fact you're in Europe or in South America, it could be the standard is 50 cycles. The point being that the frequency doesn't change over the long term, so that the metering results are usually done by quoting just the impedance and assuming that the system frequency remains the same. Of course, a purely resistive load has no reactive component, and its impedance is simply the reactance of the resistor in ohms. In other words, the impedance of a resistor is equal to R. Since inductors drop voltage in proportion to the rate of change of the current, they will drop more voltage for faster changing currents and less voltage for slower changing currents. What this means is that the reactance in ohms for any inductor is directly proportional to the frequency of the alternating current. The exact formula for determining this reactance is given by Z, which is equal to the reactance X with a lowercase l, which is 2 pi times FL, where pi is just the 3.14159, F is the frequency in cycles per second, and L is the inductance in henries. Since capacitors conduct current in proportion to the rate of change of the voltage, they will pass more current for faster changing voltages as they charge and discharge to the same voltage peaks in less time, and less current for slower changing voltages. What this means is that reactance in ohms for any capacitor is inversely proportional to the frequency of the alternating current. In other words, the impedance of a capacitor is equal to X with a small letter c, sometimes denoted with a lowercase c, and it's equal to 1 over 2 pi fc, where again the pi is 3.14159 and the frequency is given in cycles per second, and c is the capacitance in farads. Note that the relationship of capacitive reactance to frequency is exactly opposite from that of an inductive reactance. Capacitive reactance in ohms decreases with increasing AC frequency. Conversely, inductive reactance in ohms increases with increasing AC frequency. Inductors oppose faster changing currents by producing greater voltage drops. Capacitors oppose faster changing voltage drops by allowing greater currents. Alternating current in a simple impedance circuit is equal to the voltage in volts divided by the impedance in ohms, just as a direct current in a simple resistive circuit is equal to the voltage in volts divided by the resistance in ohms. This leads us to an extension of Ohm's law for AC circuits. Impedance is related to voltage and current just as you might expect, in a manner similar to resistance in Ohm's law for DC circuits. But this time we're dealing with phasors, which are vector quantities and have to be governed by the laws of vector analysis. The EMF, or voltage, is equal to I times Z, where I is the current and Z is the impedance. I also is equal to E over Z, and Z is equal to E over I. All quantities are computed and expressed using vector, not scalar rules. We encounter a measurement problem if we try to express how large or how small an AC quantity is. With DC, where quantities of voltage and current are generally constant, we have little trouble expressing how much voltage or current we have in any part of the circuit. But how do you grant a single measurement of a magnitude of something that is constantly changing? One way is to express the intensity or the magnitude, also called amplitude, of an AC quantity is to measure its peak height on a waveform graph. This is also known as the peak or crest value of an AC waveform. Another way is to measure the total height between the opposite peaks. This is known as peak-to-peak measurement, or P to P value of an AC waveform. Another way of expressing the magnitude of a wave is to mathematically average the value of all the points on the waveform graph to a single aggregate number. This amplitude measurement is known simply as the average value of the waveform. If we average all the points on the waveform algebraically, that is, to consider their signs either positive or negative, the average value of most waveforms is technically zero because all the positive points cancel out all the negative points over a full cycle. However, a practical measure of a waveform's aggregate value, average, is usually defined as the mathematical mean of all the points' absolute values over a cycle. In other words, we calculate the practical average value of a waveform by considering all the points in the waveform as positive quantities, as if the waveform looked like this. The average value would then have some value other than zero that would be related to the intensity of the wave. This is called the mean average value. So far we have looked at three ways that we can measure the intensity of an AC waveform, whether that be current or voltage, we can simply measure the peak or the crest or the amplitude of that wave, or we can measure a quantity that is peak to peak, or we can take the mean average as a quantity that measures the intensity of the AC wave. The good news is really these are all related to each other in the way they can be just scaled one to the other. In other words, they vary directly as each other. So one can be converted to the other by simply multiplying by a scaling factor. The thing or the trick we have to know is which one we're dealing with so that we can make that conversion, or we can deal with the actual measurement and it can be useful to us. As we communicate the value of voltage and current with others in the industry of electrical power, as well as their related quantities of power, energy, ratings in different elements, we have to ask ourselves how useful are using any of these terms, and is there some way of measuring the values that is the most useful way? The question was asked and answered a long time ago, and the answer was the RMS value. Before just jumping to the definition of RMS, which by the way is mathematically related proportionally to the other ways of describing the waves, such as amplitude, peak, peak to peak average, and mean average, let's go through the logical steps of getting there. Starting with two simple circuits, one DC, one AC. That is, each with the same load, but one driven by DC source and the other driven by an AC source. When we close the switch on the DC circuit, the bulb will light with an intensity that is dependent on the resistance, R sub L, of the light and the DC current. Now, let's close the switch and adjust the AC current to the light bulb with the same intensity. That is to say, both loads, both lights consume the same average power. So we now ask ourselves, what is that AC current? We can come to the conclusion that if the two bulbs light to the same brightness, that is, they draw the same average power, and the key here is they're drawing the same average power, then it's reasonable to consider the current IAC to be in some ways equivalent to the current IDC. So, what is that value of IAC? It would be useful if there was some meaningful way to calculate it, so let's go there. If an AC supply is connected to a component of resistance, say R, the instantaneous power dissipated is given by the power equation I squared R. If we plot I squared, the instantaneous current, which itself is a sine wave, it is always positive because plus I times plus I is positive and negative I times negative I is positive. It does go to zero, but never negative. Remember that the instantaneous power dissipated is given by the equation power equals I squared R. Now the peak or maximum value of I squared is shown here and labeled I squared max. The mean or average value of I squared is shown here, and it is exactly I squared max divided by 2. Remember now that the instantaneous power is given by I squared times R for the resistive load. If we wanted to find the average power, we could find it by simply multiplying the average value of I squared times R such that P average is equal to I squared average times R. But we know that I squared average is equal to I max squared over 2. So the average value of power, P average, is equal to I max squared over 2 times R. We just saw from the previous slide that the average power can be calculated by I max squared over 2 times the load resistance. Let us define a current that, when used to calculate power, gives us the average power. In other words, when that current, we'll call it I subscript defined, is squared and multiplied by the load resistance, will give us the average power. This means, of course, that I defined squared is equal to I max squared over 2, which is the mean of the current squared, or the mean squared current. Therefore, the square root of the mean squared current equals that defined current, I subscript defined. Another way of stating it is the root mean square of the current. So we just discovered what the value of I subscript defined is. It is equal to I max divided by the square root of 2. We call this current I RMS, or the root mean square, and it is 0.707, the value of I max. 0.707 is just 1 over the square root of 2. This is another more useful way to describe an AC quantity, voltage or current, and of course it can be converted to other AC quantities terms such as the amplitude or the peak to peak or the average, just by scaling the value up or down. In this case, we could take I max and multiply it by 0.707 and come up with the root mean squared. But the root mean squared current can give us the average power consumption. And you'll see in later slides that when we use RMS values for current and for voltage, that we can use them to calculate average power. Looking back at the question we ask ourselves, what is the value of IAC? Well, IAC is now, we can say, equal to IRMS, which is equal to 0.707 times the peak value of our AC current, which is equivalent to the IDC dissipating the same amount of average power. Using the RMS current and the load resistance, the average power can be calculated by using the formula P is equal to I squared R. Similarly, we can define the RMS value for RMS voltage, which is 0.707, the peak voltage for AC voltage. In the next chapter, we will show that if the RMS value of current and voltage are used, we can use all of our previously established formulas to calculate power. But this time, we are calculating the average power. Also, because we are simply using a scaling factor for the current and voltage, that factor being 0.707 or 1 over the square root of 2, then all of the equations involving Ohm's law hold true if we use RMS values for current and voltage. As well, all of the rules for mesh analysis and theorems can be used with RMS values for current and voltage, keeping in mind that all quantities are computed and expressed using vector, not scalar, rules. This is the end of Chapter 2.